have started your life, so keep quiet. Keep.
Good afternoon, everybody. Good afternoon, everybody. Okay, we are going to continue from where we stopped the last two. Chemical reaction as 2. Okay. Last time I was looking at the rate of chemical reaction, we defined the rate of chemical reaction, and also we talked about rate curve and the property of the rate curve. That was going to be ended the last class. Okay, today we are going on to collision theory, which is very integral part of rate of chemical reaction. Because it's from this that we'll be able to learn why certain reactions are faster than the other. Why certain reactions are faster than the other. Why certain reactants react faster than other forms of the same reactant. Okay, what is collision theory? Yes, somebody can stop. What are you saying? For what? I can't hear you anymore. Let me define from there. We are talking about for a reaction to actually go through, the particles or the molecules of reactants are required to what? Collide with one another. They are required to collide with one another such a way that they collide with an energy that must be equivalent to the energy barrier for the reaction to go through. What do we call this particular energy barrier? The energy barrier is regarded as the activation energy. So we can define it again to say that if a reaction to occur, the particles of of the reactants must collide with a minimum theory. So for any form of collision that occur, that in that collision the minimum required energy is actually reached, such collision is called effective collision. It's called what? Effective collision. That means a collision can be ineffective in terms of activation energy. Another one part that actually determines effective collision is the orientation of the particle. So effective collision doesn't just depend only on activation energy. Even if activation energy is reached, but the orientation of the particle is wrong, then we are not going to have the reaction going through. Then it will cause an ineffective collision. What do I mean by that? Let's take for instance, we all know that NaOH, right? NaOH together. Okay, for NaOH, we have added to HCl. This particular reactant cell, we can depict them to be in terms of ionization of OH minus, such that we have H plus here and Cl minus. For the interaction of these have to interact with this, while these interact with this. But in this is actually looking this way. So it's interacting with H plus here. This one is OH minus. This particular group, by the time it's going to collide, this one is to collide with this. If this collide with this at the end point of hydrogen here, if the collision is happening in between there, reaction will not go through. Why? Because hydrogen is not meant to bond with what? Hydrogen on this facet here. Rather, it's supposed to happen, for it to go through, it has to look at this way, such a way that the collision will happen between this. So it's at that point that H2O can form in process. I believe from the back there you can see what I've written there. Okay, and you are quiet. Okay, what I'm saying is that when OH minus is to react with H plus, these two molecules are to collide, and these two ions are to collide. We have OH minus. Now, if the collision happens at this particular point with H plus, this reaction is not going to go through. Even though the minimum amount of energy is being reached, this kind of collision will be ineffective because there will not be any formation or any form of reaction happening between the two. Rather, where the facet of bounding rate for hydrogen ion here, which we call the proton, supposed to be at the end point of what we call it, or like this, such that the collision should happen here. If the collision happen at this point, at this orientation, we are going to have H and O like this, making what? H2O. Although this bond is not linear, just forgive for that. This particular bond is going to form this way as a result of the what? Unshared pair of electrons, or what we call the lone pairs of electrons in the outermost shell of the central atom, oxygen. So that is what is going to happen. That is what we regard as effective collision. So what determines effective collision now? What are the two factors? Orientation of what? Of molecules, yes or no? Orientation of what? Molecules or particles. We can pick particles because particles cover for both molecules and ions or atoms, yes or no? Orientation of what? Particles, and then activation energy. What determines effective collision now? And activation energy. So that is what we are talking about under collision theory. So I believe that we stated the theory already. We've not stated the theory. Okay. For a chemical reaction, let's write. This states that for a chemical reaction to occur, the particles of the reactants must collide for a chemical reaction to occur. The particles of the reactants must collide with the minimum energy called the activation energy. The minimum energy called the what? Activation energy. The particles of the reactants must collide, and this particular collision must possess what? Minimum required energy called what? Activation energy. Full stop. Any form of what we call it, collision that leads to chemical reaction is called what? Effective collision. It's called what? Effective collision. Any form of collision that leads to chemical reaction is called effective collision. It's called what? Effective collision. Full stop. That leads to chemical reaction is called effective collision. Effective collision depends on what are the two factors we mentioned the other time? Orientation of particles and what? Activation energy. Effective collision depends on what? Orientation of particles and what? Activation energy. Effective collision depends on orientation of particles and what? Activation energy. Now, what's activation energy? Again, activation energy is the minimum required energy. Is the minimum required energy that must be possessed during collision of particles for a reaction to occur. The minimum required energy during collision of particles for a chemical reaction to occur. Activation energy is the minimum required energy. It is the minimum required energy that must be possessed by particles, possessed during collision of particles for a chemical reaction to occur. Full stop. Are we there? You are confused, as that? I said activation energy is the minimum required energy that must be possessed in collision of particles for a chemical reaction to occur. Full stop. We always regard it as the energy barrier. It is the energy barrier that must be overcome. It is the energy barrier that must be overcome for a chemical reaction to occur. For a chemical reaction to occur. It's the minimum required energy, the other time, yes or no, that must be possessed by particles during collision of particles, for a chemical reaction to what? Occur. We can also say that it is the energy barrier that must be overcome by the particles that are colliding for that reaction to occur. Do you get that now? Do you get the concept? Okay. Are we good to go? Are we okay? Okay. Who is saying no? Okay. So, for a particular rate of reaction, for you to determine if the reaction will be faster than the other, in terms of activation energy, we look at the magnitude of the activation energy of such reaction. When the activation energy is lower, the reaction is bound to occur at faster rates compared to the one that have high energy barrier or high activation energy. And that is how catalyst is able to work effectively. What do catalysts do? It lowers the activation energy so that the reaction is going to be able to occur at what? High rate. The speed of the reaction will now what? Increase. Do you understand it now? Write notes. The higher the activation energy of a reaction, the higher the activation energy of a reaction, the slower the rate of the reaction. Let me write on the board. My vice versa there. We are talking about the lower the activation energy, the faster the rate of what? Chemical reaction. The faster the rate of chemical reaction. But the higher the activation energy of a reaction, the slower the rate of reaction and vice versa. That is what inhibitors, promoters actually bring to a chemical system. They work on these particular forms of activation energy, ensuring that it's being raised for inhibitors so that the reaction rate will be slower or totally fused out, because the activation energy is now too high for the molecule to reach. You understand me now? But if the reaction is now finding difficult to occur spontaneously on its own, if the catalyst enter into the system, it lowers the activation energy so that the little collision that we are having within the system can actually reach the activation energy easily. So such reaction will proceed. Do you get what I'm saying now? That's what we call in the as promoters. Okay. Now we move on to factors affecting rate of chemical reaction. Factors affecting rate of chemical reaction. What are the factors affecting rate of chemical reaction? I'm going to itemize them out. Number one, we have what? What is it? What is it? Okay, nature of what? Is it reaction? Of the reactant? Yes. What is it? Concentration. You can bracket in front. Okay. Then number 3 is what? Temperature. Okay. Number 4, pressure. Number 5, what is it? Surface area. Number 6 is what? Catalyst. Catalyst presence. Yes or no? Another catalyst present, we can have a special form of catalyst which is called what? Light. Light presence or presence of light. Some persons can place this as number 6, but number 7, sorry, but I rather place under catalyst because light serves as what? Catalyst. Just like the way we cannot be placing heat separately there. Heat is also a what? Catalyst. Yes? pH. Okay, pH of the solution. No. Now, like we are talking about, a pH, the pH of the system can also serve as catalyst. You understand what I'm saying now? But that particular pH, remember that a substance that is pH, that causes the pH to be raised, is not taking part in the chemical process. Yes or no? Okay. Any question? Any question? Now let's explain all this. How this actually affects the rate of chemical reaction in practical terms. In practical what? Terms. Nature of reactant. When we're talking about nature of reactant, wake up that person. When we're talking about nature of reactant, we are simply talking about condition like states of the state of matter of those particular particles or reactant involved. What is state of matter? What are the states of matter that we have? Solid, what? Liquid, and gas. We know fully well in solid state surface area is reduced, so reaction is tending to be what? Slower. While in gaseous state, molecules are actually divided apart from one another such a way that there are enough surface area for collision, and at that particular point reaction tends to be what? Faster. So we can depict it in terms of nature of reactant. Solid, in terms of rate of chemical reaction now, solid is lesser than liquid, and liquid has lesser what? Rate of reaction compared to what? Gases. On general note, other conditions might be involved here that can actually change all this. Remember, we are just talking about one out of them now. Other conditions are still there that can still affect this particular rate of what? Reaction, apart from just the nature. You get it now? So that means we can, if you want to put it back, reversal, if you put gases first, it will be in greater form. J is greater than liquid, and liquid is greater than what? Solid. That is, in terms of rate of reaction. Rate of reaction is greater in gases than in liquid, and rate of reaction in liquid is greater than in what? Solid. That is what we mean by that there. I hope that is clear, right? Are we clear with that? Okay. Who is saying no? If it's no, raise up your left hand. Is that your left hand? You never know your left hand from your right. Okay. Now let's move on. Concentration of reactants. The concentration of reactants. The more the number of particles or number of molecules that we have, the tendency for more collision to occur, and in that wise we have more likelihood of what? High rate of what? Reaction. So what are we saying? The higher the concentration of reactant, the higher the rate of chemical reaction. And the lower the concentration, the slower, not lower. You understand it now? The slower the rate of what? Chemical reaction. That's it. So temperature. What is temperature defined as? I want you to define temperature to me in listen. Do you define temperature in terms of state of the body, but define temperature in terms of energy? What's temperature now? Yes. Under kinetic theory of matter is what? Is the average kinetic energy of the molecule or particles of that system or that body. The measure of average kinetic energy. Emphasis on what? Kinetic energy. And what is average kinetic energy? Is dealing with energy in what? Motion. That means the particles are moving. The higher the speed, the higher the what? Kinetic energy. So whenever you introduce temperature, you allow temperature, the bodies to actually gain more temperature, gain heat, sorry, don't let me say gain heat, the temperature will be raised. That means the kinetic energy of the system increases. Yes or no? Kinetic energy of the system what? Increases. And when the kinetic energy increases, that means we are talking about the speed of molecules what? Increases. That is, we have more tendency of what? Collision. More collision per second. So at that particular point, the rate of chemical reaction is bound to what? Increase compared to before. Because as they gain energy, higher kinetic energy, that means they are possessing higher energy. As temperature increases, higher energy is being what? Reached. Then it will be easier for them to reach the what? Activation energy. Do you understand me now? The energy barrier will be broken easily. So at that particular point, we say that the higher the temperature, the higher the rate of what? Chemical reaction. And the lower the temperature, the slower the rate of chemical. The slower the rate of chemical. The slower the rate of chemical. Okay. Very good. So please, if anybody is sleeping and the person is Muslim, we take the person out, we give you mark and you start praying. Very good. Okay. So that is the whole thing. It's not punishment, it's part of prayer. So we move on. Pressure. I think at this particular point, we have to go back to Gay-Lussac law of pressure under gas laws, right? Do you remember that? Gay-Lussac law under gas law, right? Pressure majorly work for gases, gaseous reactants. Are you getting what I'm saying now? Now, if you go back to Gay-Lussac law of pressure, which is called the pressure law, you have pressure is proportional to temperature, and in direct proportionality, what happens? As one increases, the other increases. Yes or no? That means as temperature increases, pressure what? Increases. And as pressure increases, temperature. So in a gaseous system, in gaseous reactants, if pressure is increased, the temperature of the system bound to increase. And when temperature increases, what do we say the other time? Higher the what? Rate of what? Chemical reaction. Do you remember this equation under that? So this is for pressure law. I know that some of you did not do it in your school. Yes, you did not do this in your school. Hey, forget about that. In chemistry, you did not do it. Only sometimes in physics that you actually treated it. Forget about that. Some of you know. Yeah, I'm not saying all of you. Emphasis on some. So if you want to defend your conscience, you know, and defend it. Okay, what I'm saying is that as pressure in gases increases, we have temperature also increasing simultaneously, and when that happens, the rate of chemical reaction is bound to what? Increase. So the higher the pressure, the higher the rate of chemical reaction, and what? Vice versa. What do you mean by that? Turning it upside down. Yes or no? Are you getting what I'm saying? Okay. So surface area is the next one. Are you with me? Are you following? Okay. Remember that in all this, there is an embedded, what do you call it, factor, which you call orientation. Yes or no? Which you call what? Orientation of what? Particles, are we? Yes or no? And activation. Again, orientation of what? And activation. Thank you. Okay, let's move on. Surface area. Surface area will actually give a view to number of particles that are exposed for collision. Number of what? Particles that are exposed to what? Collision. The higher the number of particles exposed to collision, the higher the rate of chemical reaction, because that means you have more particles colliding at once to actually knock on the activation energy door, and majority of them, if they are able to go over that, then they go. Yes or no? So the higher the rate, the higher the surface area, that means the larger the surface area, the higher the rate of what? Chemical reaction. And the smaller the surface area, the lower the what? The slower the what? Rate of chemical reaction. And that one boils down back to solid, liquid, and gas. But now let's talk about it in terms of surface, what do you call it? Talking about the area exposed. In a solid block, this way, the internal particles, only the surface particles are exposed to collision. Yes or no? Yes or no? And at the same time, it might be one end of the block that is just colliding. So the one that are at the surface are the one undergoing collision, and at that particular point, it's not to be compared to where we have in liquid that at least we have enough area to stay interact, compared to now in gases where particles are now far away from one another. That means there is more penetration in between the particles of that particular substance or that particular chemical for it to actually collide with another opposite particle. And at that point, the rate of chemical reaction is higher in gases compared to in liquid and compared to in solid, just the way we have it here. Now we can have different types of solid based on modification of this particular surface area. Now if you are talking about block, we can have block form. Yes or no? Yes or no? We can have it in granular form, granules. Yes or no? And we can have in what? Powdery form, powder or tack. It can be in form of tack, because when we talk about tack, we're talking about powder. Are you gonna say now? Yes or no? Are you getting that? So in this one has higher surface area. This is a medium surface area, and smaller surface area. So you are expecting that rate of chemical reaction is expected to increase from block towards powder, and decrease from powder towards block. You get it now? Are you getting it? It's supposed to increase from block towards powder, and decrease from powder towards block. And one of the common question that usually being asked, especially for people who are writing O-level examination, they will ask you sometime if iron wool, iron filings, and iron rod are to be combusted or reacted with oxygen, which one will burn faster? It is the wool. It is the what? The wool represents, it's not a powder form, but now it is having more shattered, particles far away, detached from one another, and lighter compared to the iron filings. The iron filings resemble the granule forms, while the rod resemble the block form. Do you get the concept now? Are you with me? It's a common question in your examination that you can easily just tackle, and it's straightforward. So the one of wool is expected to react faster than that of filings, and the one of filings are expected to react faster than the one of rod or block form. You get it? Are you clear with that? Are you clear with that? Okay. So now let's write also on catalyst. Presence of catalyst. Presence of catalyst. Let's write. A catalyst in a reaction alters the rate of the reaction. What by alter? What by alter? So that it alter, it change the rate of reaction, yes or no? And the change might either be what? Slow down or what? Or increase. Are you getting what I'm saying now? Alters the rate of reaction by impacting the activation complex of the reaction. By impacting the activation complex of the reaction. By impacting the activation complex of the reaction. A positive catalyst, paragraph. A positive catalyst lowers the activation energy of the system. A positive catalyst lowers the activation energy of the system, thereby increasing. Remember the other time I said that the lower the activation energy, the faster the what? The rate of what? Reaction. Yes or no? Is that what we established from one part of the beginning of the class today? Okay. So a positive catalyst lowers the what? Activation energy of the what? System, thereby increasing or speeding up the rate of the reaction. Increasing the rate of the reaction, thereby increasing the rate of the reaction, thereby speeding up the reaction. So what will the negative catalyst do now? What will the negative catalyst do now? It will what? Decrease the rate of the reaction. You get it now? Any question? Any question before we move on? Any question before we move on? Raise up your hand if you have any question. Okay. Now we can have different form of catalysts. We have the chemical catalyst, which are other chemicals that can be introduced to the system, to the chemical system. Are you gonna see now? We have heat, which is thermal catalyst. Are you gonna see now? Heat as catalyst, thermal catalyst, and we can have light what? Catalyst. Light what? Catalyst as light. All this, if you notice the what we have made mention of, are they not forms of energy? Are they not forms of energy? Simple as that. So we are introducing an external energy into the system. Are you gonna see now? Either in light form, either in what? Chemical form, and either in what? In thermal form or heat form. Example of a light catalyzed reaction is photosynthesis. Also reaction of what do we call it? Silver bromide in photographic plates. Yes or no? That is light catalyzed reaction. Thermal catalysis too. Okay, another form of light reaction, we think we made mention of it in last class when we were talking about halogenation of alkane in the presence of UV light. Yes or no? Then we have thermal catalyzed reaction, where heat is actually used to speed up the rate of reaction. All forms of thermal decomposition falls under this. Thermal what? Decomposition reaction. Thermal cracking under what? Hydrocarbon, right? Petroleum, sorry. Yes or no? Thermal what? Cracking. Do you remember that? All those ones are example of thermal catalyzed reaction. Chemical catalyzed reaction, like in other process, we use what? Ion filing. Yes or no? Ion what? Filings. Yes or no? Ion filings Fe is solid form for their findings is introduced to other process in order to catalyze the reaction, to make the reaction go through. Somebody is talking about medium the other time, medium what do you call it, pH? Yes or no? In your stomach, in digestive tract, the biological processes that go on there, they occur under different what? Medium. Under what? Different medium. The mouth is slightly basic. And I say slightly, I mean faintly what? Basic. Somehow that we can even relate it to be neutral form. That means if the condition of the mouth is being raised more than that, you even find out that the reaction there will not be able to work. Why? Because the enzyme or the biological catalyst that's supposed to even work there will not be able to function under that condition. Do you get it now? You don't need to function under that condition. In your stomach, is what? Acid. It's acid. When I say acidic, I mean extremely acidic, not slightly acidic. Extremely what? Acidic. While the one in other parts in your intestine, large intestine, a part of large intestine, they are basic. They are basic what? They are basic medium. They are basic what? Medium. So some of you might be asking, what is the condition in your anus? Get inside here and check it out. Okay. So that is that. Okay. Continuation with explanation on catalyst presence. So if we have a reaction system, let's draw for what do you call it? One form of a reaction, either exothermic or endothermic. Can I have just that? No, they want there. So, please get just start for me from there. You just start the back there. Get out of stuff for me. Madam, sit down. Sit. Get the duster. Okay. If a reaction complex is looking this way, initially, what kind of reaction can be represented this way, even before labeling? This is what? H what? You say what? Exothermic. Okay. HP. Why this is the point of what? Activation what? Energy. Yes or no? By the time it's going to be catalyzed, the reaction complex is going to look this way. Okay, even let me draw it within. For this is non-catalyzed. Then if you have it this way, now look at it there. You can see, does it affect this one affect the heat of reactant? Does it affect the heat of reactant? Does it affect the heat of product? What does it have things to do with? The energy what? Complex. Yes or no? The energy what? Complex. Such a way that the activation energy is reduced from here to what? To this particular point. So this one shows what? A catalyzed what? Reaction. So this is the, and this is what? Do you get that now? Are you with me? So in this, it is catalyzed there. Why? Because it lowers the what? This one is a positive what? A positive catalyst is at work here. Yes or no? What happened? It lowers the what? It lowers the rate of the reaction. It lowers the rate of the reaction. Now let's open to our past question. Madam, let's open to our past question and let's answer one or two questions pertaining to this there. And this one actually serves us a good foundation. This one actually serves us a good foundation towards chemical equilibrium. Towards chemical what? Equilibrium. There is a way we can actually relate this with reactants and with products. Are you get what I'm saying now? With reactants and with what? Products. Okay. Where's the duster? So please, let's bring out our past question as we just round up the whole part here. Okay. We can have rate of reaction. For rate of reaction, we can say it is proportional to the concentrations that we want to actually relate it to, such a way that we are talking about the fact that listen please, we are talking about that if we have reaction A plus reaction B plus reactant B to give you C plus D. This one is small letter A, which are the concentration of A, concentration of B, concentration of C, and concentration of what? D. This reaction can be related to just the reactant because this direction of what? Reaction. This direction of what? Reaction. Such that we can say that R is proportional to the concentration of A, then concentration of what? B. Do you get that now? Concentration of A, concentration of what? B. And at that particular point, we can say fully well that R is equal to K, concentration of A, then A, concentration of B, then what? B. And if this particular reaction, we want to look at it in terms of the product. In terms of what? Product, I mean. So we can say R is equal to K, then C, concentration of C, then D, concentration of what? D. In an equilibrium process, when this reaction is at equilibrium, that is, rate of forward reaction is equal to what? Rate of what? Backward reaction. We can. No, we are done with catalyst. Not quite long now. We just switched to what we call explanation on the rate. Type of catalyst. Okay. R is equal to what? This is what you call, if this particular rate 1 is equal to rate 2, that means the reaction is at what? Is at equilibrium. So we can say fully well at that particular point, K, concentration of A, concentration of what? B, is equal to K, concentration of C, concentration of what? D. Do you get that now? Are you with me? So that if this one now, this is K1, this is what? K2, or we call it KR, K of reactant, and K of what? Product. Abi? Yes or no? So that if KR over what? KR over what? KP, it will be equal to, that means this one coming down, this one will remain here, it will be what? C, concentration, D, concentration, over what? A, concentration, and what? B, concentration.
Please, Mr. Alade, tell you to give me one brand new good marker, black. Sharp, black, new marker.
Go and do that, be fast.
Go and get marker for us.
Okay.
See what you're writing again.
Okay, let's pause a bit. Like I said, our past question, we are going to answer that. Open there and let's wait. We answer. Okay, what's the question there? It's a diagram. Okay. Just don't worry, we're going to draw the diagram on the board. Once the marker is back, we'll be able to finish up the explanation of it. I just want to lead us into order of reaction and then finalize it with a big template for our chemical equilibrium. So by next class, we are going to discuss equilibrium in detail. Yes. Who is asking question?
The product will be over.
It's the product. It's not product that is up there. This one is not product. No. It will be KR over KP. That's same thing in but two of them are united together as one. That's why we say that forward reaction. K of forward reaction. K, this is K for forward reaction now. K for backward reaction will now be KP over KR. Are you gonna say now? Okay. Where is this man? Let's wait for him to come around.
Hello, shut up.
Where are you? Hello? Okay, let me just recalibrate these ones. Okay, now looking at this here, are you with me? Please wait them up. Don't pity them. You're not pitying me here. Okay. Now looking at this here, we said that KR over KP. This is what you usually talk about as your what? Equilibrium what? Constant. And this is for forward reaction. Now it depends on how you want to see it. Now here we take this one as the reactant because it's written at the left hand side, right? And it is in order of this arrow. I don't understand now. But immediately we look at this particular arrow coming back like this. These ones become reactant and this one become the what? Product. So if you have already picked side already, saying that this is reactant and this is product, if for forward reaction, the equilibrium constant will look this way. But for backward reaction, the equilibrium constant will now look at this way. Kp over what? Kr, which will now be what? Concentration of A. Concentration of what? B over what? Concentration of what? C. Concentration of what? D. Do you get that concept now? If you are confused, better speak up now. Remain silent forever. So what's the confusion? Where?
Why is clear equal to C?
Okay, look, see, KR is not equal to that. Look at this place. What we call R1 rate 1 is equal to what? For this, that's for forward what? Reaction, Abi? Not for forward, not it's for in terms of looking at rate of reaction from the reactant what? End. Yes or no? From the product end, we have R which is equal to what? K and this, Abi? What we call it, at equilibrium, this particular, if the system is equilibrium, this particular forward reaction will be equal to what? Backward. So at that particular point, we can now say that R1 is equal to what? R2. What is R1? This. KR, K what? P. Why? Because this is in terms of product. This is in terms of what? So KR A this is equal to, because that's R1, Abi, it's equal to R2. What's R2? KP this. Now if you place this 1 over 1 over 1 and cross multiply, this KP is the one we want to move down here. This one we also want to move down here. So KR will now be over what? KP, and we collect consider on one side, this one up here over what? This. That's what we have done there. But remember, we put forward this particular KR to be on top. That means we are looking at it from the reactant end. That is what? In terms of the what? Forward reaction. This one will form your what? Equilibrium constant. This will form your what? Equilibrium what? Constant. And at the same time, we can have it, when we have it this way, we can say that if we are looking at the backward reaction, that means in terms from the what you are already labeled, because you are already picked side from the beginning, that is your product, whereas your product is now reacting back to become what? The reactant again. Yes or no? Is that not the meaning of the backward arrow? From the point of the product, we can now have KP up. Remember when you are looking at it from reactant, the other KR is up, Abi. What will happen? KP come up. That is inverse of this, Abi. So inverse KP over KR. Then we must have inverse of this other side too. Whatever happened to this side must happen to this side. So this side turns over again. And that's how we are having this. Yeah? Okay. Okay. Now, in terms of order of reaction is simple. Order of reaction, we are talking about what your rate of reaction actually depends on. What your rate of reaction actually depend on. It depends on the constant and also depend on the concentration that we have in the reaction. When your rate of reaction is only dependent on K, this kind of reaction is zero order reaction. Zero order. What do you mean by zero order? Listen to me. Remember the other time we have R is equal to K, concentration of A, concentration of what? B. Yes or no? Now let's talk about this one. K Arabi. Now look at this place here. Okay, then let me prove because we don't say K rate 1. K concentration of this. Now look at this place here. For we to have K alone, that means A must be what? 0 and B must be what? Anything raised power 0 is what? So R is equal to what? K times 1 times what? And R is equal to what? K. That is zero order. What is that zero order? The concentration what? 0. Concentration of the what? The particles or the substances involved, it has become what? 0. Do you get the concept now? Do you get it now? At the beginning of any chemical reaction, before the reaction proceeds, before it starts occurring, in terms of the product, if you have to look at the rate of reaction, the reaction only depends on the constants, because the concentration of the product will be what? 0 before the reaction starts occurring. By the time the reaction finish occurring, what will happen? The concentration of the reactant, if you know reactant is in excess, we have equal what do we call it? Stoichiometry ratios that have to react, and they finish reacting. What will happen? The reactant will become what? 0, and the product will become what? Maximum. Yes or no? Yes or no? I'm not talking about backward reaction. I'm talking about just a kind of reaction that can only proceed in one direction. Are you gonna say now? At that particular point, it will only depend on K. Now, if concentration of if small letter A is equal to 1 and small letter B is equal to 0, we can have it, or we say that A equal to 0 or B and B equal to what? 1. At that particular point, we can have our rate. We're rating as this: K concentration of A, which is what? 1, abi? Concentration of what? B, which is what? 0. So our R will be only depending on one of the reactants. Either A, when A is 0, it will now this one will now be what? B here. Yes or no? Is that not it? When the rate of reaction is dependent on the constant and one of the reactants, where the concentration is just 1, that kind of reaction is a first order reaction. It's what? It's what? It's first order reaction. First order reaction. So that is what we have in there. You get it now? If you have any question, raise up your hand. What's the question? Okay, the concentration here is what determines the order. Here, right here, A plus B is equal to 0. That's why it's 0 order. Are you gonna see now? Right here, A plus B is equal to what? 1. Yes or no? Is either 1 plus 0 or what? 0 plus. That is what? First order reaction. I mean the molar ratio there. Are you getting what I'm saying now? So if A plus B is equal to 2, it will be second what? Order what? Reaction. And how can A plus B be equal to 2? It can be A is equal to 1 and what? B is equal to what? 1. That is what? 1 plus 1 equal to 2. Abi? Also, it can be A is equal to 2, B equal to what? 0. Or A equal to 0, B equal to what? 2. If in any of these cases you add A plus B together is equal to 2, we say it's what? A second order reaction. We say it's what? Second order reaction. Any question again? Any question again? And now some of you, your problem is that you have not been taught this part. All this part, you just keep lumpa to the next one. You now be wondering what's the order of reaction? What are we seeing here? Yes? As you write up, okay, I'm writing up. You to write up this one. Won't you write up this? Okay, but can you see this one here? Precious, can you see up to this particular point? No. Yeah, stand up a bit. Stand up a bit. No, she's not short. In short. In short. You are not short. Don't mind them. In short, you are not short. Short. Every shot is short. Okay. First order what? Reaction. Of first order reaction, we have the concentration to be what? 0. Abi? Second order will be what? We have the molar stoichiometric ratio to be what? 0. Abi? But when second order is what? Equal to 2. Third order will be what? Equal to what? 3. And so on and so fifth. And so on and so fifth. Fourth. Okay. And so on and so forth. Any question? Okay, you have a question the other time from the past question. So this has served as this serves as template for us into chemical equilibrium. It's distracting you. Okay. Remove his head. That's where his distraction is coming from. Wake her up. Melody. Who is singing for you in sleep? Okay. Okay. Now let's look at questions on this. Let's check out questions on this directly from your exam. Madam, please start from the most recent years first, and let's do it towards the back. 2025, 2024, 23, 22, and so on and so forth. Yes? Please, it is now. If you have any question that you can ask your question, everybody can benefit from the explanation. You don't have what? Data for subscription. You don't have 2024?
I have 2024.
Okay, start from 2024. You have 2025, yeah? Okay, please read from 2025. Then if we take over from that 2024. Question 16. Wait. Are we still writing this one? Okay, let me leave it there. Question what? 16, yes.
17.
JAMB what? What here? 17 and what?
22, 25, and 39.
Now listen. All this, number 17, yes?
Number 16.
Okay, 16.
If a gold and silver bar
If a gold and silver bar
are tied together for years, and gold has occurred,
which process has occurred? This one is not directly on rate of chemical reaction. This one is about diffusion and what movement of particles. Yes or no? What process has occurred is simply what? Diffusion. Why is it diffusion? That which one involve all state of, but in osmosis it involve what state? Liquid, yes or no? Or what? Fluid, liquid majorly. Are you gonna say now? Solvent. All right. Solvent particle, dissolving solute. That is what I'm saying now. Okay. So what option is that? Option A. Then number 17 is what? Number 17 is what? Has it ended? Number 17 is what?
Okay, which of the following contribute least to the greenhouse effect?
Which of the following contribute least to the greenhouse effect? We've discussed about this now. Under pollution. Or is it question of pollution you are looking at? Okay. Continue. Which of the following contribute least to greenhouse effect? Okay.
Carbon sequestration.
Carbon what? Carbon. Sequence, abi? Sequestration. Carbon sequence, movement of carbon cycle. Okay.
Methane emission.
Methane emission, abi? Combustion, yes. Contribute least. Now listen, if you deforestate, that means if you remove trees from ecosystem, what will happen? We have less usage of what? Carbon dioxide. So amount of carbon dioxide in the atmosphere will what? Increase as a result of respiration for what? Animals. And at that point, carbon dioxide contribute directly to what? Greenhouse effect, global warming. Then for combustion, what is the end product of combustion? Complete combustion is what? CO2. And if it is incomplete, CO, this one will combine with oxygen in the atmosphere to form what? CO2. This one still boils down to what deforestation is doing. Yes or no? Then methane emission. Methane is also a very common gas that actually contributes to what? Greenhouse. Why is methane contributing to greenhouse effect? CH4 in the atmosphere will react with oxygen and will form what? CO2 and what? H2O. And at that particular point, it increases the global warming. But in carbon sequestration, what we are talking about? We are talking about how carbon enter into the what do you call it? That's the way we do refer to this kind of system. We call it we call carbon something cycle, biogeochemical cycle. The biogeochemical cycle, as this one is talking about how carbon is entering into biogeochemical cycle and how carbon is being removed from the biogeochemical cycle. So in carbon sequestration, we are going to have how carbon dioxide enters and how carbon dioxide is what? Being removed. So this one contributes less to that particular process. This one contributes less to that particular process because it's only majorly about how carbon is entering and carbon product is what? Removed, is taking off the what? Process. So this one is talking about how carbon dioxide is the product of respiration and is being used up by what? Photosynthesis. Are you gonna say now? And so on and so forth. You get our concept now? Okay, so the option there is what? Option A. Then number 18 is what?
21.
Okay, 21.
The equilibrium constant.
The equilibrium constant.
Since it is affected by.
No, this is on equilibrium. We've not even talked about equilibrium.
Yeah, let's move to the next one.
What do you call it? Equilibrium constant is actually affected by several factors, not several as much because they are not that much. I don't understand now, but this particular principle, how they actually affect chemical equilibrium of the system, is actually given called Le Chatelier, which is called the Le Chatelier's principle, talking about where equilibrium constant is going to shift to and where it's going to go to. One of these things that doesn't affect Le Chatelier, doesn't affect the chemical equilibrium system, is catalyst. It doesn't affect constant. Are you gonna say now? It doesn't affect what? Equilibrium constant. Do you get me now? But temperature do that, pressure do that, concentration do that. Are you gonna say now? So for this, for all this, we only calculate usually for KC. Equilibrium constant due to what? Concentration and what? KP. Are you gonna say now? This one here majorly function for solid dissolved, solid that have been dissolved in form of solids or liquid dissolved in form of solid, where we have mole per what? DMQ. Why this one fall what do you call it? Function majorly for what? Gases. Are you gonna say now? Gases. Talking about pressure of gases in what? ATM. What's ATM? Automated teller machine. Atmospheric pressure. I don't know, atmosphere. Atmosphere. It's measured in atmosphere. So it's talking about atmospheric pressure. So ATM. So KP. KP for gases. KC for what? For what? Concentration. Molar what? Concentration. That is why whenever you are writing any derivative for all these KC, KP, you remove anything like pure liquid, pure solid away from such. You remove what? Pure liquid and what? Pure solid. You remove it from the expression. Like water, if water is part of the whole thing, you don't write it as part of your equilibrium constant. You get it now? If a solid is present, get out of here, kick it out like kick a maze. I get what I'm saying now? But if it is gas, in terms of you will put it. But if it's out of KP and concentration is available, it's not involved. But if it is out of KC and gas is involved, the gas is not reckoned with because it doesn't contribute to that. When we get there, you will get that one clearly. Let's move on.
Number
22.
The rate of the chemical.
The rate of what?
Chemical reaction.
Yes.
Can be expressed as.
The rate of the chemical reaction can be expressed as
A product divided by time.
product divided by what?
Time.
Product divided by time, yes.
Reactant times time.
Reactant
Divided by time.
times time.
Rate equal to mass divided by time.
Rate equals to what?
Mass divided by time.
Mass divided by time.
In change in concentration divided by time.
Where is it? Rate is equal to what? Change, Abby. In concentration over what?
Time.
Which one out of them all? This. Change in what? Concentrate. You cannot be talking about mass. We don't know change in mass because time, if it is that we are talking about a complete process now where we have initial mass and so that the reaction will go to completion using up the mass, it's still change in mass. Are you gonna say now? But the only thing that the change in mass will now be equal to what? The initial mass, Abi? Because the final mass is zero. You get it now? So it is much more, or if we use this one is the best way to calculate for what? Rate of chemical. Remember our definition of rate of chemical reaction that is so a change in what? Abi? Yes. Rate at which something is used up. I don't understand now. Let's move on.
Okay, 25.
25. What's the okay? This is D. 25. Yes.
Value of an equilibrium constant.
The value of an equilibrium constant.
Subscript K subscript
K substitute that is KC. KC. Okay. Skip it.
Yeah. 39.
39.
2 SO2.
2 what?
SO2 gas
2 SO2 gas
plus O2 gas.
plus O2 gas. Hope is not on equilibrium too.
Standard
The
standard unit of formation.
okay is on it. Okay, to give what? 2 SO3 what? Gas. The standard heat of what?
In the reaction,
Standard heat of formation, yes.
290 for minus 297 kilojoules for the first one.
Minus
297 kilojoules.
kilojoule, yes.
And the second one minus 396 kilojoules.
Minus 300 what? 96 what? Kilojoule, yes.
What is the equation of the reaction?
Wait. This one is for all these, Abby?
Yes.
Why this one is for what? Minus what? 300 and what?
Okay, 396
396 what?
kilojoules.
Kilojoules. Is that how it is there? Is that how you find the what? Heat change. Now remember that heat change is what? Heat of what? Minus heat of what? So change in it is now what? What's heat of product here? 96, right? Okay, yeah. This is 2 moles here. 2. It's supposed to be well stated here that SO2 is this. And what are you now reading? Respectively, SO2 and SO2. What are you now reading, Philip? Ma. SO2 and SO3. So that is we multiply by 2 minus 2 bracket what? Minus 297. Two times this is what? Minus what? 792. Abi? Minus 2 times this is what? Minus what? 594. So our change in need to be equal to what? Minus 792 plus times minus 594. So our change in need is equal to what? Minus what? 198 kilojoule. Yes, per mole now. That's why we are doing it, changing it. The change in it of your system before you leave today will be, it will be endothermic, it will be positive. Because we gain heat from the environment. Although it is actually going to be exothermic because your body is giving out heat by sweating and it will cause cooling of your what? System. It will be exothermic. Are we together? So we need 2 points of ours. We have been able to convince you. Thank you. Okay. Are you done?
Where now be laugh? Okay. Now be laugh here and do ambo. So you said left corner. Life refuses to go on life. Life refuses to on life. So, the thing wants to life. Let it life.
Qué va a ser cosa,